Okay, so let's start. So we introduced unified process last time, so let's continue. So unified process is use case driven. So what is a use case? A use case is a specific functionality of the system. So an actor, it represents either the user or some other external system. And a use case is a functionality required by a user, by an actor. So it functions that add value for the user. That is the reason why you're developing the system in the first place. So a use case model is a complete system functionality. It includes all the use cases. So the use case model is used to reach agreement with the client on the system's required functionality. It represents a contract between the client and the developer. So at the end of the day, when the project finishes, can your system perform any of the all the use cases specified in the requirements document? If yes, then the contract is fulfilled. Otherwise, you didn't do your job. So they help project managers plan, assign, and monitor tasks. That is, use cases you may prioritize the use cases and focus more resources on the most important use cases. Use cases drive the development process. That is, you transform the use case model into analysis, design, and implementation models, and you should have traceability. That is, you should be able to point to some analysis model or design model and say, which use case is this for? So use cases support seamless traceability between models. It acts like a central glue across all the different models. So here's one example use case model for a ATM machine. A bank customer uses the ATM machine to withdraw and deposit money from and to accounts and to transfer money between accounts. So we can identify three use cases here: withdraw money, deposit money, and transfer money, right? So that is the whole use case model consisting of three use cases. So then from this use case model, you can develop analysis, design, implementation, and deployment models, eventually test models. So that's why we say a unified process is use case driven. So you start with the use cases, then you develop the detailed models for each use case. So, and then you can feedback to the use case model. So while you're developing the detailed models, perhaps you discover some new use cases. Perhaps you modify the existing use cases. So another characteristics of unified process is that it's architecture centric. So architecture is just like a traditional, in its traditional meaning of architecture, it's a high-level outline of the form of the software system. It's a skeleton of the software system. Describes the most significant static and dynamic aspects of the system, including subsystems, interfaces, and dependencies between them. Provides different views of a system. Compare this to a building, right? A building, you have a structural view, you have a mechanical view, electrical view. So the same system can have different views for different expertise. Describes the foundation of the system. That is the basis on which the system will be developed. It's the skeleton where you attach the muscles later. the key use cases determine the architecture. Normally, 5 to 10% of the use cases are the key use cases. The rest are secondary use cases. So the use cases describe the function of the system. Architecture describes the form of the system. So the function is the what the users want. The form is the how it's accomplished. So, for example, in an architecture, in your course project is this 3-tier architecture. You have a database, web server, and user interface. So that's how you accomplish how the system is structured. But the use cases are that what you can do with the system. Register for a course. That's the key use case. And registers, add and delete courses. That's another use case. So what versus how? So typically the client doesn't care about the how. He only cares about the what. It's the job of the software engineers to design a good architecture to implement, to accomplish the use cases. The goal is to have a stable architecture by the end of the elaboration phase. Remember the 4 phases: inception, elaboration, construction, and transition. So by the end of the elaboration phase, your system architecture should be stabilized. So use cases drive software architecture, and in turn, architecture guides the use cases. That is, you first use the most significant, the key use cases to derive a architecture, and then based on the architecture, you guide the development of other secondary use cases. Architecture has a set of constraints and enablers. That is, all these elements have an effect on the architecture, including system software, that is operating system, database management system, middleware for communication, or database or business transaction, legacy systems, standards and policies. Does the organization require Windows or Unix on the desktops? Non-functional requirements, that is, this is versus functional requirements specified in the use cases, what the system is supposed to do. Non-functional requirements is how well the system does it, like response time. When you click a button, how long does it take to get back a response? Or throughput, or scalability, how many users can the system handle? These are non-functional requirements. Distribution needs, that is, does the system need to be distributed? Does the organization have 2 offices, one in the US, one in Hong Kong? If that's the case, then your software system must be able to handle the distribution. Experience plays an important role in designing the software architecture. So from previous architectures developed for similar projects, and architectural patterns. So this is so-called design patterns. If you have heard of it, it is essentially a set of patterns summarized from many years of practice to be a good practice for designing architectures. So obviously, client server is a good pattern to use. A layered architecture where you have system is structured into multiple layers. For example, network protocol stack is a 7-layer protocol. Object broker is another pattern. So all these are really part of the experience that you learned from either yourself within the organization or by the software engineering community at large, as documented in many books. So these guide the architecture design. So architecture baseline is the skeleton of the system. with all critical parts but few softer muscles. So it consists of early versions of all the models, from use case to analysis to design to implementation, etc. But these are very rough, very early versions of these models. So, and you will evolve the architecture baseline gradually as you go increment it into future iterations, and eventually deliver a full feature product. So here's the 4+1 view of the unified process. So as you can see, the use case view sits in the middle. That's why it's called use case driven. So it is the end users, analysts, and testers are interested in the use case view. It describes the system functionality, what the system is supposed to do. And then logical view describes the system structure. It consists of the analysis model and design models, how the system is structured, all the class diagrams, the entities in the system and how they're related. Implementation view consists of the implementation model and test model. These are interested in by the programmers and software engineers and project managers. So I think if I click on it, we'll see some examples. So here's the example I showed you earlier, the use case model for the ATM machine. It has 3 use cases: withdraw money, deposit money, and transfer money. And then the logical view consists of analysis model and design model. So as you can see, it really describes the architecture of the system. So as you can see, the customer is the little stick figure representing an actor, and he interacts with the ATM machine via 2 interfaces. One is the cashier interface, one is the dispenser interface. And withdrawal is this withdrawal is an intermediate intermediate layer, and account is the database layer. So this is the classic 3-tier architecture, where perhaps customer is here, interacts with the ATM machine user interface, go through, perhaps this is the web server or this is the database server. So, and design model is a more detailed version of the analysis model, where you refine the interface classes into more concrete classes. So the cashier interface is one class, gets mapped into 3 classes. A card reader, where you insert your ATM bank card and it reads your card. A display asks you to input some options, and keypad where the customer can use to input options. And dispenser, that is the cash dispenser, gets refined into 2 classes: dispenser feeder and dispenser sensor. That is, it counts how much money has been dispensed. And the withdrawal class gets refined into a whole bunch of classes in here. So essentially consisting of transaction manager to manage financial transactions, account manager to check the account information, does the account have enough money or not, client manager, and the account essentially gets mapped into the persistent class, that is the database class. So we'll discuss analysis and design models in great detail in the next chapter. So for now, I just need to understand this is part of the logical view. That is, this describes the system structure. the high-level architecture. So the implementation view is for the programmers or software engineers. So you have the design model. Each of the design model class, each of these came from the design model: client, manager, dispenser, feeder, etc. And you actually implement it into a C. Suppose the implementation language is in C. Then client.c file is a file, and this class resides in the client.c file. And these three classes reside in the dispenser.c file. So, and when these two files are compiled and linked together, you get a client.exe file. So you have this executable. It's a stereotype indicating that this particular class represents an executable, and this is a file, and this is a file. So, and this resides. So all these are stereotypes. Stereotypes are the annotations you add to your class diagram to indicate special meaning, to give special meaning to the classes. So these are conventional stereotypes. You can define your own stereotypes. So process deployment view is for system engineers, for the IT staff. That is, the system has been developed. Now you need to deploy it onto the client side. You need to determine the system topology, delivery, installation, and all the IT job. So here's the deployment model, where you have a database server, ATM database, and you have a application server connected via intranet within the bank, and then via the internet they're connected to the ATM client. That is the software running on the ATM machines, and eventually interacting with the human customers. So when you are deploying the system, you need to put the database onto the database data server, put the all the intermediate classes into the application server, and the user interface classes onto the client machines. So that's deployment. And finally, process view is it shows the system processes. So here the process means different thing from a software development process. It really means threads. That is, the operating system manages how many processes they're scheduled by a round robin or other stuff you learn in the operating systems course. So they have an effect on the system performance, scalability, and throughput. So the system integrator cares about these attributes. These are so-called non-functional requirements of the system. So we don't have an example of a process view. In the UP, the software development is primarily a model building activity. So from use case model to analysis design model to implementation test models, and finally to deployment model. So each view is associated with one or two different types of models. So iteration and increment. So iteration is one step through the workflow. That is one horizontal step from requirements to analysis to design to implementation. And increment is the growth in the product from iteration to iteration. That is, if you recall the unified process, so each vertical line from requirements down to software QA, this is one iteration. And as you're growing from iteration to iteration, from left to right, that's increment. So unified process is iterative and incremental. That is, each iteration results in a working product. In the early iterations, you have very rough baselines, prototypes, and eventually you refine the product into a more complete product as you go to different increments. Each increment establishes a new baseline for the system. That is, you never go back to a previous increment. You always go forward. A baseline means that you start from here. When you fall back, you always fall back to the baseline. You don't fall back to any earlier baselines. Iterations and increments must be controlled to be effective. By control, we mean planned. So you need to plan the iterations very early, so you have concrete milestones. So developing the system in small steps allows us to mitigate risks. That is, we can identify and deal with the biggest risks as early as possible, because you have a early executable system. Develop a robust architecture. That is, the iterations help identify the right architecture. Oftentimes, if you're drawing it on paper, it's hard to design good architecture. But if you're developing the system incrementally, then it's easier to arrive at a good architecture. Get feedback early from the client, because you have something early to show the client. Plan better, because you're developing things piece by piece instead of having this big bang integration in the end, which is a bad approach. Integrate system parts more easily, because you're doing integration all along the way at each iteration, and attain early learning. That is, you can go through the workflow many times, so that the developers can gain exposure to all the development tools and systems very early, so that they have the expertise in the next iteration. And also, it's good for training new team members. So how to select what to put into an iteration? Use cases that extend product functionality, that is, and highest risk use cases. So you focus on the highest risk use cases, do risk analysis, and mitigate risks early. And then you gradually add more functionality as you are going to a later iteration. So again, you'll see that it's use case driven, where the use case define the goals and drive the work of the iterative and incremental process. So each phase concludes with a major milestone. So phase, you have 4 phases, right? So inception phase, where you reach agreement among the clients and the developers on the system's lifecycle objectives. That is, agreement on what we should build. So for the registration system, you want to build a system that allows students to register for courses, and a few other functionalities. So that's after the inception phase. The elaboration phase is to agree on the viability of the lifecycle architecture, business case, and project plan. That is, determine if the system is feasible in terms of technology, cost, and time. So you need to estimate the cost and present a business case. Is it worth it to develop the system, to spend the money and time? how much business benefit does it bring. And project plan, you need to plan out in terms of time and budget. A construction phase is when you at the end of the construction phase, you should reach agreement on the acceptability of the software product, both operationally and in terms of cost. That is, at this point, you should have finished implementation of the system. You've gone through the analysis, design, implementation, testing. Now you need to show it to the clients and determine if it's acceptable or not. Does it fulfill the contract or not? Did you build the right product? Did you build it right? Did you build it right? So the right product is a product that the client wants. Did you build it right means that does it have a lot of bugs? Does it work? So sometimes you may have a perfect software system with 0 bugs, yet it's not the right product because it's not what the client wanted. So both of the right product and built right are important. Is the cost acceptable, right? So does it exceed the budget? The transition phase is when you reach final agreement on the acceptability of the software product. That is, the software system is transitioned to the client side, and it's in operation and it works. That's when the client finally signs off. So let's review unified process. So you have different iterations. You develop the system iteratively and incrementally. Each iteration is a complete round from requirements down to design, implementation, testing, and software QA and management. And as you go along different iterations, you shift focus. So in the very first iteration, you only do some requirements and perhaps a little bit of analysis and a little bit of design. And as you go to more iterations, you shift focus to gradually to design and implementation and testing. So that's when your focus shifts. But it doesn't mean that it's waterfall. It's not waterfall because you're doing everything a little bit at every iteration. And at the end of every phase, you have a milestone. So inception phase, elaboration phase, construction phase, and finally you're done. So the milestones are what we mentioned just in the last slide. So inception phase, agreement on the lifecycle objectives. Elaboration phase, determine feasibility, and construction phase, determine acceptability. These are milestones. And each iteration, from iteration to iteration, is an increment. So you're growing from iteration 1 to iteration 2. That's an increment. So each iteration is assessed at its conclusion to determine if there are any new and missed requirements. Any new existing requirements have been changed, and how the remaining risks affect the project. So you can see risk analysis, which is really inherited from the spiral process. We do not start the next iteration unless the goals of the current iteration have been achieved. At each iteration, we need to do regression testing to make sure that what have worked before still works. Regression testing is when you run the old tests on the new modified system to make sure that any old tests that have passed before still pass now. That is, the new stuff you added didn't break the old functionality. The planning is iterative, just like the development. That is, you're not doing a whole grand plan in the very beginning. That's waterfall. In UP, you're planning it iteratively. As you go on, you modify your plan. So ultimate success is when a sequence of iterations that always move the project forward and never having to go back. So that is, once you reach the end of iteration, you go on to the next iteration. So this sounds a little bit like waterfall, but it's not waterfall because by never having to go back, we mean that you never have to go back from a later iteration back to a previous iteration. Never go back from right to left. But at every iteration, you're going from requirements to analysis to design to implementation. So if it's waterfall, then you're not allowed to go back to requirements or to an earlier workflow. But here, we're constantly going back to earlier workflows, but at each iteration, we have a concrete goal, and we go on to the next iteration. So summary, a software development process needs to consider both management and engineering issues. So management issues include software QA and project management, which will be discussed at the very end of the course. So we are mainly focusing on engineering issues. Software development process needs to consider the characteristics of the organization, including its size, access to users' clients. If it's an in-house project, you're developing, say, the budget control system for the engineers themselves to use, then it's very easy access to the users. But if it's a contract project, the access to users' clients may be harder. Need for formality. At the one extreme is a waterfall, which is a very formal process. At the other extreme is the extreme programming or agile process. Extreme programming is one form of agile process, whereas extremely informal. You just go in and hack the code, essentially, from day one. So different projects call for different levels of formality. And a project, if it's small or large, is it vague or well-defined? Is it novel or well-known? So if it's vague, which means that the requirements are not very clearly specified, then waterfall is infeasible. If it's well-defined, then perhaps waterfall is okay. If it's small, then perhaps you can try an agile process. If it's large, then agile doesn't work. So if it's a novel project that has never been done before, then perhaps you need a different process. So people, including availability of expertise and skill of developers. So UP is object-oriented. That is, it emphasizes object and class-based design and incorporates best practices of previous processes. It's a blend, a hybrid of the previous processes. Integrates management and engineering activities. That is, at every iteration, you're going through all the engineering workflows. In addition, you're going through the management workflows. It can be adapted for different types of organizations, projects, and people. So it's only a template. It's not a recipe. So it's very adaptable. But in general, it is a very heavyweight process. If it's a relatively small software organization, it's not likely to adopt UP. So, any questions on UP? Okay, good. So now let's move on to requirements. So here's a cartoon, Dilbert cartoon. Dilbert is a software engineer. and his boss is this pointy-haired boss. So boss says, "What's your project 4 months behind?" Dilbert says, "I still don't have the user requirements because she's a complete nut job." Boss says, "It's your job to manage that process." Dilbert says, "I complained to her boss, who promptly misinterpreted the problem and ordered her to work in the wrong stuff." And Dilbert says, "Then every member of her family got a serious illness and she got called to jury duty. She promised to give me the requirements this afternoon." And then the client says, "It's too hard to come up with my own requirements, so I just copied the requirements from another product. Dilbert says, "Is the other product similar to what you want?" The user says, "What are you going with this?" So this essentially shows the clueless user. That is, you're trying to gather requirements from the user. The user is perhaps a secretary or some people who are not very technically savvy, and he doesn't really know the requirements, write down the requirements document. He doesn't know how to do that. So it's a difficult job. So that's why requirements elicitation is not an easy job. So here's the learning objectives. Understand the role and importance of requirements capture, the major activities, and at the end of the requirements, we produce a document containing two models. One is domain model, one is a use case model. Domain model describes essentially the database. Use case model describes the use cases, as we discussed earlier. Capture the data requirements and the processing requirements of a system. So data requirements are the domain captured in the domain model. Processing requirements are captured in the use case model. Capture and specify user interface requirements. And design acceptance tests to validate the system requirements. That is, if the test pass, then the requirements are fulfilled, and the contract is fulfilled. So, requirements capture. So, a requirement is a feature that the system must have, or a constraint that it must satisfy to be accepted by the client. So requirements capture, also called requirements gathering or requirements elicitation, is the process of learning about the problem that needs a solution, that is the application domain, specifying the required features, constraints of the system in a way that the client and the user understands and can approve. So in a way that the client understands, which means that it should be in natural language, it shouldn't be in computer jargon. And the reason is that the client needs to approve it. It serves as a contract between the developers and the client. The goal is to assess and specify the behavior of the final software system. Before everything else starts, you need to specify what you want to know where you are going. So, there's a saying that if you don't know where you're going, you'll never get there, right? So, the results of requirements capture also help in project planning. That is, if you know precisely what you're trying to accomplish, you can plan the resources better, estimate time and budget costs. So this slide essentially it emphasizes the importance of requirements capture. Here's the statistics on the various reasons for project failure. So highlighted in red are all the reasons related to requirements: incomplete requirements, lack of user involvement, unrealistic expectations from the user, changing requirements, system no longer needed. So failure to do requirements capture well is the leading cause of project failures and problems. Here's the cost to fix a defect. If the baseline is in the requirement stage, if you have a defect in the requirements, to modify the requirements, if that cost is 1 at the baseline, and then design stage you have 1.3, coding stage you have 2, and system test stage you have 13, and in the field use stage you have 80,000. So that means that if it costs $1 to fix a defect in the requirement stage, it costs $80,000 to fix it. We'll find it out during field use. It's because you need to do product recalls, and perhaps it's very costly in terms of both the money and your company's image in the consumers. So that's why good requirements capture helps reduce the cost of software development. So you try to fix bugs early. So why requirements capture is difficult? So the aim is to build the right system, the system that meets the user's needs. Requires collaboration of several stakeholders, usually with different backgrounds. So a stakeholder is someone who holds a stake, someone who cares about the project, has a reason to care. So there's often a knowledge gap. That is, there are some things that you know that the clients don't know, and some things the clients know that you don't know. So there's knowledge gap. Clients are experts in the application domain, and you are the expert in computers, in programming. So the challenge is how to bridge the gap. So requirements capture is mainly about communication between the developers and the clients, users. So a failure to communicate and understand each other can result in problems and failures. So the software engineer needs to bridge the gap by learning about the application domain and discovering appropriate requirements from the client and user. It can be very difficult, as we showed in the cartoon, where the user really it's hard to get anything from him. So application domain can be very complex. So if you're developing a financial transaction software, you need to learn all about the financial market. That can take a learning curve. So transforming vague ideas into precise requirements. That is, the client, you may learn these things from the client by conversation, not even the formal document. And you need to transform that somehow into these models, use case model, analysis model, etc. So choosing appropriate representation for specifying requirements so that the clients can understand and approve them. So for this purpose, the use case model is a perfect representation because it's very intuitive. It's understandable by anyone. So software engineer may need to educate the client user to understand the requirements and to tell them what is technically feasible. The client may want everything, but you need to give them the reality as to what is achievable within a given budget and time. So requirements, one is to understand the application domain and identify user needs. That is the first step. So every software project is different. So, and one software company may be developing software for many other application domains. So for each project, you need to learn the domain, collect data on the system requirements, collect data on system constraints, in terms of a budget and cost, defines development effort scope, define what is should be developed and what should not be part of the project, and define the system design goals. As we mentioned earlier, different systems have different goals: reliability, dependability, time to market, etc. So you need to choose and prioritize among the different goals for different projects. Determine the risks of developing the system. That is a risk analysis, including economic risks. That is weigh the development cost versus the ultimate benefit. That's the business case. Operational risks. That is determine if you can implement the solution, which may depend on the availability of skills in the organization, among the users also, if the users are computer savvy enough to operate the system. Legal risks, liability, that is obviously if you are developing a control system for a car, then if your software system has a bug, you'll perhaps be held liable for any damages. Technical risks, that is the technical merit of the system concept. Is it feasible or not technically? Organizational risks depends on the developer skills and your current level of expertise within the software development company. So document the system requirements. There are two parts of documents. One is the static part that describes the static persistent data, the database schema essentially. In here we call it domain model. It essentially is the same as the database schema. We just call it a different name. Plus specifications and dynamic model, that is the use case model. So static model is just the database lying there. Dynamic model is the active software system that operates on the database and do something real, like withdraw money or register for courses. So that's processing plus constraints. Then validates the system requirements, set criteria for user acceptance of the completed system. That is the job of the acceptance tests. That is, at the end of the requirement stage, you design a set of tests. And then at the end of the development, you run the tests. And if all the tests pass, then the user should accept the product. So, system requirements specification SRS documents the requirements, serves as a contract between the client and developer. So here's another cartoon. Alice is another software engineer. Alice says to the user, I will need to know your requirements before I start to design the software. And I'll let you read it yourself. So another clueless user, essentially. So user says, I'm trying to make you design my software. And I won't know what I can accomplish until you tell me what your software can do. And Alice is very annoyed. And then eventually the user says, can you design it to tell you my requirements? So actually, this depicts a very realistic situation. The client, the user, doesn't know what he wants. But if you show him something, he'll tell you if it's what he wants. So it highlights the importance of prototyping and having an early executable version of your system to gather client feedback. So this guy here essentially is having difficulty, but he said, I won't know what I can accomplish until you tell me what the software can do. So that can be fulfilled with a prototype. So understanding the application domain and identifying user needs. So collecting data on application domain requirements and constraints. So this may include examining existing system. Perhaps you have a legacy system that's already working, but the client wants to have a better system. So investigation includes existing documentation. They may not be available, so if they're available, then it's a good source of information. Charts, procedures, forms, etc. That is the business procedures. So what does the user do daily without the system? Manually, perhaps. Then if you understand the manual procedure, then you can design your system to automate that procedure. Observation of work practices to check out what happens in the work environment and perhaps do some of the work. That is, you sit with the client, with the user, during his or her daily work and observe what he does, and in order to understand the workflow, the practice of the user. Interviews via either personal interviews or questionnaires to a large group of users. And prototyping by having a rough prototype, you can show it to the user, and the user will tell you which part he likes, which part he didn't like. Shows both the interface and the functionality. So in doing so, it is important to elicit problems, not solutions. So sometimes the user may tell you, we need a teleconferencing system for communication among our offices. Perhaps you should rephrase the problem into our offices are not communicating effectively. Perhaps teleconferencing system is a solution. Perhaps there are better solutions, like a group work environment, some group collaboration software. So you try to elicit problems and discuss different solutions instead of just getting a solution from the user, which may not be the best one. Distinguish needs from wants. That is something that's critical, something that's nice to have, bells and whistles. So try to prioritize needs and put the nice to have into a low priority list. Challenge clients' users' view of the world. That is, clients, users may have been doing something for many years, and you may need to challenge him. They may say it's always done this way, or everybody does that. Then you may have to ask, is it really everybody or just most people? So effective communication skills are required to gather requirements. So that's why you always emphasize communication skills in your job applications and interviews. Define the scope of the development effort. That is, what is inside, outside the system, and who decides. So define the design goals. What qualities do we want the system to have? For a safety critical control system, you want reliability, dependability, and for perhaps cost effectiveness is not a concern, or time to market is not a concern. If you're developing the aircraft control software for Boeing, if it takes 10 years, it takes 10 years. You don't want to rush it. But if you're developing a mobile game software, if it takes 10 years, your company will be out of business very soon. So determine the risks of developing the system. Risk analysis. Risk assessment. So should we build the system? So what risks are there? Economic risks. So we need to weigh the cost, both development and operational costs, versus benefits. Is it worth it? Tangible versus intangible benefits. Tangible benefit is something that can immediately bring in profit. Intangible benefit is perhaps something that not obvious, but it helps improve your customer service, helps improve your organization's workflow, and eventually it will result in benefits, but it's not easily measurable. Technical risks include availability of technology. That is, if you're using the newest, latest programming tools or operating systems, do they have bugs? Actually, in the aircraft control systems, the microprocessors they use are typically more than 10 or 20 years old. Why? Because these chips are tried and true. The old chips have been used for many years and there are no bugs. They don't want to use the latest, newest Pentium chips on the aircraft because it may have bugs. Even though these minor chances of bugs doesn't really matter for a desktop workstation, it matters a lot for aircraft. So typically what they do is that they actually stockpile many chips, old chips from a company produced on the same fab line on the same day to make sure that there are no manufacturing variations. And then they use this batch of chips for, say, 20 or 50 years and never change anything to make sure that there are no risks in terms of the chip design. So availability of technical resources, that is, do you have the expertise to develop the system? Operational risks, availability of skills to operate the system. So if the users are completely not computer savvy, if the users are 80-year-old grandmas, then if you have a complicated system, then he or she may not have the skills to operate the system. The fit into current work practices, that is, you don't want to redesign the work practices. That is the daily workflow of the user. Users want to continue to do what they have been doing, but in a more efficient way instead of changing their work practices. And organizational risks, that is politics, training, user acceptance. When you develop when you have a project, there are always politics involved. So which project gets the budget, which doesn't have the money to build it. So legal risks, including liability, copyright, patents, etc. So especially in the software area, copyrights or patents are very prevalent problems. So requirements, there are two parts. Static requirements described in the persistent data, the database, described in the domain model, and dynamic requirements described in the use case model. So the domain model describes the important concepts of the application domain as classes. For your registration system, the domain model consists of students, professors, register, courses. These are the application domain concepts. Allows the development of a glossary of terms, or also called data dictionary, for communicating among everyone on the project. To have a consistent terminology. For example, you may call a professor an instructor or a lecturer. But if you design your database model to call the class a professor, then you have a consistent term to use among everyone. Dynamic requirements include functional requirements, that is, the interactions between the system and its environment, independent of its implementation. So in the student registration system, the environment is the actor, the human student or professor. The system is the software system. And you only care about if you can register for courses. You don't care about the implementation of the system. Is it a 3-tier architecture? Is it Windows? Is it all these details do not matter at the requirement stage. Non-functional requirements describe user-visible aspects of the system. They are not directly related with the functional behavior of the system, including response time, throughput, security, etc. So throughput is how many user transactions can you process per second. Response time is how long does this particular request take to handle. And security is the login requirements. Is the system secure? So in your project, essentially we don't emphasize security because we allow anyone to register for an account, either a professor account or a student account. But in a realistic system, perhaps you need to take security into account to limit who can register as a user. Pseudo requirements describe restrictions on the implementation of the system imposed by the client, implementation language, OS, platform, etc. So perhaps the client organization has the requirement that it has to be implemented on Windows using C#. The requirements should only state what is needed, but not how it's done. So how it's done is the job of the later analysis and design stages. In practice, requirements often has a mix of what and how, but ideally it should only consist of what. So the unified process in the UP, we discussed the requirements. Essentially, it is done across all the stages, all the phases. 3 of the phases: inception, elaboration, construction. So these are the workers and artifacts. So the system analyst is this overall responsible person who should take care of a domain model, that is the static requirements, use case model, the dynamic requirements, actors, who are the actors in the use case model, glossary, and domain analyst is the person who is responsible for understanding the application domain. And use case specifier is responsible for doing the use case specification. User interface designer is responsible for designing the UI and prototyping. And architect is responsible for architecture description. So oftentimes these roles are played by the same person or a group of people. So these are the activities. The system analyst finds classes and associations, identify the application domain concepts, and detailed class associations is done by the domain analyst. That is, you identify how the classes are associated with each other and their multiplicities of association. And system analyst find actors and use cases. And architect prioritize the use cases, which we don't do in this course because our use cases are very few. We don't have to prioritize them. But in the real, when you have many use cases, you need to pick out the important ones, and structure the use case model, put them into packages, and use case specifier designs the detailed use cases, fill in the details, and a user interface designer prototype the user interface, and they feedback to the requirements to validate the requirements. So our focus is everything except the prioritized use case. So domain modeling is this part, finding classes and associations and filling in details. And use case modeling is the rest. So we'll first focus on domain modeling, that is the static requirements. So domain modeling captures the most important classes and associations in the context of the system. That is, things that exist or events that occur in the system's environment. That is, so classes and associations are found from first high-level problem statement. That is, for example, the document I gave you as your course project. That's a problem statement, which is the specification of the user's needs. And domain experts, user, by collecting data and identifying user needs. So the high-level problem statement may not be complete. Oftentimes, you need to talk with the user to gather more details. So it is imperative that this be done well so as to establish a solid foundation and to allow reuse by other systems. So it's a foundation because everything else, every later implementation design efforts depend on this domain model. It provides all the essential elements like students, professors, courses, and how they're related. So it's a foundation of the system. Allow reuse, that is, if you design the domain model well, then you can reuse it for later system. For example, for the billing system, you can also use the same domain model that you designed with the course registration system. The classes can be a business object that represent things that can be manipulated in the business, say accounts, orders, etc., or real-world objects and concepts that the system needs to keep track of. Suppliers, customers, students, professors, or events, that is aircraft arrival departure event for a aircraft control, for the airport control system, sales. So one sale is one event. It happens on a particular day with a particular amount. Reservations, etc. So all of them can be classes. So it provides a glossary of terms. So the class diagram captures all the classes, and once you fix the terminology, it can be used throughout the rest of the project. So it's described in the class diagram. That is the static system structure, which we have already discussed the basics of class diagram before. Now we're trying to show its use in capturing the domain model. So identifying classes. Naturally occurring things or concepts in the application domain. So classes often appear as nouns or noun phrases. A noun phrase is a collection of nouns. So a good student is a noun phrase, for example. Associations appear as verbs or verb phrases. And you circle or highlight in the problem statement these nouns and verbs, and you put all terms into singular form active voice. which means that singular form is when you say student registers for a course, versus the plural form, which says students register for courses. Active voice is when you say students registers for a course instead of the course is registered by a student. So identify only relevant classes and associations essential throughout the system's life cycle. That is, they will always exist throughout from design to development to testing, etc. So this leads to a stable system. So the decomposition of the problem into classes and associations depends on judgment and experience and the nature of the problem. So there's often not a single one correct decomposition. So for simple problems, it's often very obvious how to design the classes. So for your example, you have students, obviously, professor, and how they're related. But for more complex systems, you may have different ways of designing the system. So oftentimes there's no one single correct answer. Okay, so that's some silly. So next we have a large example that is the course registration system. We'll show you step by step how you go from the natural language document into a class diagram. So we'll discuss the next class.